This talk is about arrangements and combinations of objects. But what are these, and what early problems gave rise to them? What is Pascal's triangle and how did it originate? What is the binomial theorem? And what is the Manhattan problem? Such questions form part of combinatorial analysis, or combinatorics, the branch of mathematics that's concerned with selecting, arranging, listing, and counting objects of various kinds. Here we'll meet some of these, beginning with arrangements, before proceeding to combinations and Pascal's triangle. So in how many ways can a given collection of objects be arranged? Here's an ancient problem from a mathematics book from India. The Indian god Vishnu holds in his 4 hands a discus, a conch, a lotus, and a mace. How many arrangements are possible? Clearly his first hand can hold any of the 4 objects. His second hand can then hold any of the remaining 3 objects, and so on. So the total number of possible arrangements is 4 times 3 times 2 times 1 equals 24, which we call 4 factorial, written with an exclamation mark. Likewise, for n objects, the corresponding number n factorial of arrangements is n times n minus 1 times n minus 2, and so on, down to 2 times 1. And below, I've listed the first few of these numbers. 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, 4 factorial is 24, 5 factorial is 120, and 6 factorial is 720. Here's another example from India. It concerns the god Sambhu, who has 10 hands, and we're asked for the number of possible arrangements of 10 objects, ranging from a rope and an elephant's hook to a dagger, an arrow, and a bow. With 10 choices for his first hand, 9 choices for his second, and so on, we obtain the answer 10 times 9 times 8, etc., or 10 factorial, a number that exceeds 3 million. Also interested in arrangements, but in a musical context, was the French monk and mathematician Marin Mersenne of Mersenne Prime's fame. In 1636, he published a book on universal harmony, which dealt with many theoretical aspects of music. And in particular, as pictured here, he displayed all the songs formed by arranging 4 musical notes, and there are 4 factorial, or 24, of these. He then followed these with the 5 factorial equals 120 arrangements of 5 notes, and the 6 factorial equals 720 arrangements of 6 notes, pages and pages of them, all carefully written out in full. We now turn our attention from arrangements of objects to combinations. Around the 6th century BC, a Sanskrit medical treatise noted that medicines can be sweet, sour, salty, pungent, bitter, or astringent, and its author, Susruta, explicitly listed all the possible combinations of these when taken a few at a time. For 2 at a time, there are 15 such combinations, such as sweet and sour, or sour and pungent. He also listed the 20 combinations when they're taken 3 at a time, the 15 combinations when taken 4 at a time, and the 6 combinations when taken 1 or 5 at a time. In general, we let the combination number Cnk be the number of combinations when taken k at a time from a collection of n objects. So here, C62 and C64 are both 15. C63 is 20, and C61 and C65 are both 6. Much later in the 6th century AD, the astronomer Varahamihira calculated the number of ways of selecting 4 perfume ingredients from a collection of 16, obtaining the correct answer of 1820. He surely didn't list all of these combinations, so how might he have found this number? If the order of selecting the ingredients had mattered, there'd be 16 ways of selecting the first one, 15 ways of selecting the second, 14 ways for the third, and 13 ways for the fourth, giving 16 times 15 times 14 times 13 selections in total. Notice that this number is 16 factorial divided by 12 factorial. But here the order doesn't matter. The same 4 ingredients could have been chosen in any of 4 factorial equals 24 different orders, all giving rise to the same selection. So to find the number of possible combinations, we must divide by 4 factorial, giving 16 factorial over 12 factorial, 4 factorial, or 1820 as the correct answer. This is the combination number C164. And in general, the number Cnk of unordered selections of k items from a set of n objects is given by this long expression, which is equal to n factorial divided by n minus k factorial times k factorial. If now, in this formula for Cnk, we put k equals 2, we get Cn2 equals n factorial over n minus 2 factorial, which simplifies to n times n minus 1 all over 2. These are the triangular numbers because these numbers, 1, 3, 6, 10, etc., can be arranged in triangular patterns as shown. Also, if you take the dots one row at a time, you'll see that Cn2 is also found by adding 1 plus 2 plus 3 and so on. Among the properties of these triangular numbers is that the sum of any 2 successive ones is always a perfect square. 1 plus 3 is 4, 3 plus 6 is 9, 6 plus 10 is 16, and so on. You can check this by algebra, or you can see it geometrically as shown, with the triangular patterns of 10 and 15 dots combining to give the square of side 5. We'll now look at 2 important rules for combinations. Rule 1 is that for any numbers k and n, Cnk is equal to Cn n minus k. For example, as we saw with Sussruta's medicines, C62 equals C64, with both being 15. We can prove this algebraically using our formula for Cnk. But it's more revealing to note that when we choose k of the n objects, we are equally choosing which of the remaining n minus k objects to exclude. So Cnk, the number of ways of choosing the k objects to include, is equal to Cn n minus k, the number of ways of choosing which n minus k objects to exclude. Rule 2 is that for any numbers k and n, Cnk is equal to Cn minus 1 k plus Cn minus 1 k minus 1. Again, we can prove this by algebra, but instead let's look at the n objects and colour one of them red. Each of the Cnk choices of k objects must then either exclude the red one, requiring us to choose all k objects for the remaining n minus 1 objects, or it must include the red one, requiring us to choose the other k minus 1 objects from these remaining n minus 1 objects. So Cnk, the total number of choices, equals Cn minus 1k, the number of choices that exclude the red one, plus Cn minus 1k minus 1, the number that include the red one. A well-known arrangement of these numbers is the arithmetical triangle, or Pascal's triangle, named after the French mathematician and philosopher Blaise Pascal. Here, the number that appears in row n and the diagonal k is the combination number CNK. For example, in the row labelled n equals 6, the entries 1, 6, 15, 20, 15, 6 and 1 are Sussruyter's numbers. There are several things to notice here. For example, by combination rule 1, CNK equals CN n minus k, so each row can be read forwards or backwards. Also, rule 2, CNK equals CN minus 1k plus Cn minus 1k minus 1, each inner number is the sum of the two numbers above it. For example, in the row labelled n equals 7, each 35 is the sum of a 15 and 20 in row 6. We can also look at the diagonals. The diagonal marked k equals 0 is all ones. The diagonal k equals 1 then lists the natural numbers 1, 2, 3, 4, 5, etc. While the diagonal k equals 2 features the triangular numbers 1, 3, 6, 10, etc. The combination numbers CNK that appear in Pascal's triangle are often called binomial coefficients because they arise when we multiply out powers of a binomial or two-term expression such as x plus y. For example, when we multiply out x plus y to the power 6, we get the result below, where the coefficients 1, 6, 15, 20, 15, 6 and 1 are again the Sussruyter numbers. The arithmetical triangle has a long history predating Pascal by several centuries. On the left is the earliest one known by the Islamic scholar Al-Karaji and dating from around the year 1000. On the right is a Chinese arithmetical triangle from the year 1303. It actually contains an error. One of the entries in row 7 is 34 instead of 35. Many other versions appeared in Europe from the 16th century onwards, but it was Pascal who gave the first modern treatment of the numbers CNK, explaining the different ways in which these numbers can arise. His version appeared in his Treatise on the Arithmetical Triangle, which was written in 1654 and published posthumously in 1665. We conclude with a problem that illustrates the combination rules. It's known as the Manhattan problem. A grid of streets has K west to east blocks and M north to south blocks. How many southeast routes are there from the top left corner A to the bottom right corner B? In this example, K equals 4 and M equals 2, and the total number of steps from A to B is K plus M, which is 6. One such route, shown here, is east, east, south, east, south, east, which appears as EESESE, together with all the other possible routes. Now each route has 6 steps, with 4 E's and 2 S's, and the number of possible routes is equal to the number of ways of choosing where to position the 4 E's, which is C64 equals 15. But it's also the number of ways of choosing where to position the 2 S's, which is C62, and so these are equal, illustrating rule 1. And in general, the number of possible routes is likewise either C, K plus M, K, or C, K plus M, M. And if we then write n for k plus m, so that m equals n minus k, we get rule 1. We can also illustrate rule 2. Here k equals 6, m equals 4, the total number of steps is k plus m, which is 10, and the number of possible routes is c of k plus m k, or c of k plus m m, each of which is c 10 6. Now every route to B must pass through either the point X or the point Y. But the number of routes through X with one fewer row is C 9 6. And the number of routes through Y with one fewer column is C 9 5. And so C 10 6 equals C 9 6 plus C 9 5. And in general, the number of routes through X with one fewer row is C k plus m minus 1 k, which with n equals k plus m is C n minus 1 k. And the number of routes through Y with one fewer column is C k minus 1 plus m k minus 1, which is C n minus 1 k minus 1. Adding these together then gives us Cnk equals Cn minus 1k plus Cn minus 1k minus 1, which is rule 2. And with that unusual way of proving these two rules, I thank you for listening.